Hello and welcome to another Copper Show. I'm delighted to say I've got Hayden Locke, the CEO of Marimaca, with me again today. Hayden, how are you?
I'm really well, thanks, Melvin. Yeah, all going along really well. Announced a big partnership and exciting times in the Marimaca household.
Good. Well, we'll get into that a bit because what I really want to talk about today is just to kind of give a basic primer to the audience on the difference between oxides and sulfides in the copper space. And at Marimaca, you've effectively been targeting the oxide development, and you've hit some in some deeper of the drill holes in your geotech holes. You kind of hit some sulfides. Let's just kind of, in general terms, tell me a little bit about the difference between an oxide and a sulfide, please.
Well, look, geologically, the copper mineralization for deposits always starts as a primary sulfide mineralization. That is how it's placed. And what we find is as meteoric water or surface water from the surface and exposure to air hits those minerals, it turns it into and transforms it into an oxide deposit. So that's the most basic premise. Typically, what you find is oxides occur at the surface or near the surface or nearer the surface. It doesn't always have to be right at the surface. It can be undercover, as you see in very large deposits like Estimita. But in general, they tend to be closer to the surface and are therefore more typically mined as a hit. The biggest difference, though, between these two minerals is how they're processed and what you eventually do with that. So oxide copper species, many of the oxide copper species, not all of them, are what we call leachable. So they can be dissolved in acid or weak acid, and the copper ions go into solution. And then the recovery is very different to the recovery if you go through a sulfide process.
Because on a sulfide process, they don't leach, and therefore you have to treat their ore differently. You have to grind it up, liberate the sulfide mineral, and then separate that sulfide mineral away from the other minerals which aren't sulfides to produce typically a concentrate.
Exactly, and the other key difference, and you're exactly right. I was go into lots of detail about the differences in those methodologies. The other difference is at the end of our process, we are producing what's called a grade A copper cathode. That's very pure copper material. What is produced at the end of a sulfide or pyrite chalcocite mine that uses this flotation concentration is a concentrate, which is then shipped to a smelter, which is then the very high temperatures turned into various stages of product before it gets to the final saleable.
You used the word chalcocite in there, which can go both ways. It can be it's a So chalcocite's this funny mineral, which is a secondary sulfide. So the original chalcopyrite can be weathered through those meteoric and oxidizing waters, but it can reprecipitate as a different kind of sulfide called chalcocite, which is CuS, and so the copper content on it is much higher. But that can also be leached as well. So, I mean, what you also like in an oxide deposit is when you have this this enriched cap. Do you have any chalcocite in at Marimaca?
Yeah, we do. In the enriched zone at the bottom, in that area where we're getting to the depths where we're approaching that sulfide horizon, we have pretty prevalent chalcocite and cobalt. So both leachable secondary sulfide materials. They do have a longer leach cycle, and as a result, in our assumptions, we assume a much lower recovery rate for those. But yes, they do leach, and given the quantity and scale, and the fact that it's mixed with oxides, we didn't propose to float that, but rather.
And just coming back to your point about them being close to surface, effectively, when you've got a mineral deposit which has been emplaced, a copper deposit which is in place and then weathered over a long period of time, you can get the oxides forming down several hundred meters, can't you? I mean, where there's a good fracture permeability, you can get these oxidizing waters down to, I mean, as I said, a few hundred meters. And then, of course, it can be covered by later gravels or a later ash fall if you're in a volcanic region. But the oxide bodies can be quite large, can they not?
Absolutely. On the top of porphyries, they can be many hundreds of millions of tons. Certainly in IOCG deposits like what Marimaca is, well, Marimaca is kind of an IOCG ivory. We also have a very large oxide blanket on top. It's unusual, I would say, in areas where, you're right into the bedrock relatively early and typically quite hard bedrock, that you see a, 500-600 meter level of weathering like what we've seen in Marimaca. That is very unusual. We've got a 500 meter continuous column of mineralized rock, which is quite unusual, but certainly a couple of 100 meters is pretty regularly seen on the top of large scale.
Isn't that a function though at Marimaca? Because as I understand it, was oxidized in one orientation down to a certain depth, but obviously over kind of quite a wide area, and then it was tilted. And is that not what gives the 500 meters of supposed depth, but actually it's just kind of a lateral measure that's been kind of rotated around? So you can, now it's deep, but at the time it was of a level and has been rotated. Is that what you're referring to?
No, not quite, although that is certainly part of the reason why. It's like a domino effect to nowhere, as say, to the west. But the oxidation profile is really a function of the reason why Marimaca is there. We're still formulating the final thesis as to its genesis, because it is quite unusual deposit. But it is in place as a result of really pervasive fracturing of the rock. So a huge amount of fracturing through that rock all the way down, several hundred meters surface, which has allowed that surface water to permeate through the deposit. And yes, okay, some of that has been exacerbated by that domino effect. It's more a function of the reason that an unusually unique deposit in this part of the world is that really pervasive fracturing, which is caused by the regional shear forces, causing what we call a dilationary jolt, an extensional zone between two rock structures that has expanded that mass and allowed the copper-rich fluids to flow into it.
And I guess if you've got some part of kind of rotation or transpression on that structure, and you've got a brittle rock, it's going to kind of exacerbate the fracturing or kind of augment the fracturing. One of the challenges of oxide deposits generally, whether you're talking about copper or gold, is that they're normally volumetrically small, because it's only kind of they're challenged by being close to surface. You mentioned that they can be up to several 100 million tons on the top of a big porphyry system, but the amount of production today is very much driven by sulfide. Global copper production is driven by the sulfide minerals. But when you're assessing an oxide deposit, when do you know that you've got enough to kind of say, actually, we might be able to do an oxide standalone project here, or we might just have a little phase one on the oxide and then we're going to go on to the sulfide, or you might just kind of stockpile the oxide to one side and then move on to the sulfide. What can you just kind of describe to me some of the thought process around those decision trees?
Yeah, you're right. 85%, I think, or maybe even more of the global copper production comes from sulfide deposits and therefore smelting. Although there is a pretty strong push now to move back to leaching, or trying to leach those primary chalcopyrites, which is kind of the holy grail of copper. We'll see if anyone really cracks the nut on that. We've seen a few technologies that are quite interesting. In terms of project size, look, oxide projects can be much smaller. I'm not advocating that people should run and invest in small projects, because in mining, like any industrial process, scale is your friend in terms of amortizing fixed costs. There is a base of fixed costs that needs to be considered for any project that you can't get away from, minimum staffing requirements. So there is some economy of scale. But as a general rule, I would be looking at, 30 to 35,000 tons of copper production. My low end is sort of starting to become quite interesting. Once you hit 50,000 tons of copper cathode, you're a globally significant cathode producer. and that is a very nice place to be. In terms of mine life, he wants 10 years, so that puts you in the range of 500,000 tons of contained copper and upwards. And once you get north of 1,000,000 tons, the game will be a globally significant source of potential.
Sorry, just those rough sums. 10 years producing 35,000 or 30 to 35,000 tons per annum. And you talk about a roughly 500,000 tons per annum of contained copper. Is that because the recovery is likely to be 70 odd percent? Is that what you're?
Yeah, look, give or take. It depends really, and this is where we get into some really sort of quite technical areas. The biggest risk on a heap leach copper project, alongside the resource, is the metallurgical test work and understanding how it will fall on the heap, understanding variability. And I've spoken to yourself and Matt a lot about de-risking mining projects. It is fundamental to do the work, but as a general rule in Chile, copper projects are operating at between 60 and 75, 80% recoveries, depending on the mineral species and what's going in and around it and their operating parameters.
And one of the attractive things about copper oxide projects is that there's a difference in capex. Why? Can you kind of outline the key differences in capex between a kind of a sulfide operation and an oxide? What is there and what is there not in across those two process routes?
Yeah, so the mining stage is completely the same, and then you get to the primary crushing stage, which is completely the same. And typically with a copper oxide project, you will crush to a size of roughly 3/4 of an inch, and we talk about P80 since 3/4 of an inch. So what's that, about 1.5 centimeters being 80% of your material, being less than 1.5 centimeters, or thereabouts. Mixing my metrics and imperial systems. The key difference from that step is that typically with a sulfide project, you will need to grind reasonably significant finer, and that is really driven by processing phase afterwards, which is typically a froth flotation of those sulfide minerals. But you need to make sure that the sulfide minerals are liberated from the surrounding bedrock, or what we call gangue. If they're not liberated properly, the froth will not be strong enough to float the sulfide minerals, and you won't get the recovery. So the next big piece of capex is typically a ball mill, which is a very large piece of equipment, depending on mine size. Multiple ball mills, if you get up to really big projects like Cobre Panama, I know they have several enormous ball mills in parallel. And Escondido is obviously enormous. So that's the first big piece of equipment difference. That is a relatively expensive piece of kit. Also very expensive from the power consumption side. So the power consumption curve to take a rock, the same rock from 3/4 of an inch to 75 microns or even finer, is an exponential curve. So you're putting in exponentially more power to reduce the size of the microns in those that's going into your flotation plant. Then you get into the flotation plant, which is actually a plant. So there are big tanks, lots of agitators, lots of mechanical equipment, lots of piping. That's another key difference between a heap leach project, in that a heap leach is just a pile of dirt sitting on. Yes, there's civil and earthworks, which you spend up front in terms of capex, but it's much lower cost than having all the steel, piping, electrical instrumentation, monitoring, and all that sort of stuff. And in many cases, you need to have that covered.
But you need an irrigation system, don't you? Through your heap. But I guess that's not this. It's an order of magnitude different, or it's just not on the same kind of page as the piping and the circuitry and the metalwork required for a flotation circuit.
Yeah, the irrigation system on a heap leach looks like a large-scale garden irrigation system. It's just black pipes running across the top of your, depending on the system used, across the top of your heap leach, and you're running your acid material, your acid leaching liquid through there, and it percolates through the heap, and then you collect it, typically using gravity into your ponds, and then pump, ideally using gravity, into your SXEW. SXEW is different. Obviously, that's an expensive portion of our cost. Makes up about 40% of our total capital cost, or thereabouts. solvent extraction, electrowinning. So that is the key difference between concentration and what we're doing at the end. So what we have is a leach solution which has copper ions in it. It gets pumped into what's called the solvent extraction phase, where we inject or stir in an organic material which attracts the copper. Then the copper organic material is washed, and the final product is sent into the SXEW, where an electrical current is run. And it's that electrical current that causes the copper to plate
and that's the electro win. I mean, you're literally winning the copper by stimulating it with electricity.
Exactly.
And that every time I go around an SXEW plant, I always kind of slightly choke on the acid fumes. So that's an acid. A key input or a key reagent is acid in there, isn't it?
That's right. Sulfuric acid specifically, although you can use some other acids, but sulfuric acid is the most commonly used leaching liquid.
And where do you buy the acids from generally? I mean, I know that each country has its own acid balance. I've done a little bit of work on the acid balances in Namibia and the Congo and Zambia back in the in a previous life. Typically, where does the acid come from to use in the SXEW process?
Well, so acid is primarily acid supply demand balance is primarily driven by the fertilizer industry, which consumes most of the acid globally, primarily for the development of phosphoric acid. So widely used in fertilizers, and that's a real driver for the ups and downs of the acid price. Acid is notoriously bad at traveling and at storage. So you typically want your acid source relatively close to you, and you don't want to be storing it for too long because it's highly corrosive in that pure form. So the biggest sources are natural sulfur burners, which come, there are lots of groups that burn sulfur, elemental sulfur to turn it into sulfuric acid. So large scale chemical companies to sale in industrial purposes, but also in the copper industry. The other big source is smelting of primary sulfides. So obviously burning, superheating any sulfide ore will create sulfur dioxide, which can then be captured in sulfuric acid. So the biggest sources tend to be smelters and straight up sulfur burners. Obviously, anywhere there's a big footprint of copper production is likely to be a very large scale producer of sulfuric acid, and Chile is no different. So the vast majority of acid in Chile is kept internally for use in the copper industry. Maybe there's a little bit of export. Most of the acid coming up to our region is imported through the port of Meteoric, which is about 20 kilometers from southern Peru and a few other industrial sources. There is also a very large scale smelter just south of Antofagasta, produces about 800,000 tons a year of sulfuric acid. So there's plenty of sources around in Chile. Central Africa, or the sort of Zambian copper belt, maybe slightly less, but equally wherever there's a smelter, there's likely to be.
Yeah. And I've also been to some operations where they had their own acid plants. I've visited some of the uranium operations in Niger, and I've been to an acid plant. Funnily enough, in I think Marin, when they were doing the high pressure acid leach on the nickel laterites, they were using quite a lot of acid there. They had huge piles of sulfur that they were converting into acid.
Yeah, I know there's definitely a tipping point in terms of scale where it starts to make sense to buy the elemental sulfur and spend that capex. But a sulfur burner acid plant is a relatively expensive and quite dirty piece of equipment. So if you don't have to build it, avoid it if you can.
Yeah, absolutely. Just going back to the sulfide processing route, we've gone through the flotation circuit, and that, as you mentioned, has got lots of kind of piping, and there are roughers and cleaners, and then presumably that just gets filtered and packed and dried.
Yeah, correct. De-water, and send that wet tailings to the tailings facility, and then you ship out the concentrate material to whichever smelter you've got an agreement for some percentage of the contained metal barrier.
And in Chile, there's some fabulous pipelines, aren't there? Of kind of concentrate pipelines. Have you any comment on those? I mean, have you got any insight?
Yeah, well, I think concentrate is not pure metal, and so you're not getting. So in terms of the value of per ton of material sent, it's not 100% metal value. Whereas with cathode, if you send a ton of cathode, it's worth what is $8,500 today. And if you think about the cost of either trucking or training, or lower value material, it can eat into that margin pretty quickly. So transport and logistics is something you have to consider. But I think certainly in Chile, being up in the high Andes, it makes a lot of sense to use gravity and use a large scale like a slurry pipeline to get the concentrate slurry down to port where it will be exported, because it just saves such an enormous amount of costs in terms of transport, but also the capex to build out the transportation infrastructure is significantly cheaper to do a pipeline. They're very well used in industrial processes the world over, significantly reduced costs.
And they send kind of 60,000 tons per annum or more down these pipes, that size diameter, and it comes out like toothpaste. I mean, it flows like toothpaste. It's quite extraordinary, isn't it? Down to the port, and then it's dried again because it has to have a slightly higher moisture content to move through the pipes, and then it's dried again and then loaded into ships. I mean, it's quite a remarkable feat of engineering. I guess that so with the reduced capex, but potentially with the smaller scale, does that change the economic thresholds? I mean, do you think it's safe to generalize to say that you can generally get away with a lower grade on an oxide than you can on a sulfide, providing there's enough scale?
There's a lot of moving parts to that question, but I'd say in general, probably you can get away with a lower grade oxide project, assuming that you get decent recoveries, 65, 70% recoveries, assuming then you have a manageable strip ratio in your open pit, i.e. less than sort of 5:1. Assuming that you've got relatively good access to power, assuming all of those things, you can almost certainly say that you're going to have a lower grade. Although the complication is typically in flotation circuits, you tend to recover a lot more copper. Whereas you might get 65, 70%, and then in a heap leach project, you might get 90+% that contain copper, 85, 90% in a concentrate project. But I think the real kicker is on average, if you look at the industry, the average capital intensity, i.e. the total capital cost per ton of copper produced for a sulfide project versus an oxide project is about 2.5 to 1. So all else being equal, you will see a significant return on capital benefit from an oxide project, and therefore something is what we describe as much more defensive and robust, and almost certainly has a better chance of being a mine regardless of the.
And with a lower capital cost per ton, but possibly also a lower operating cost or an energy consumption, is that hard to generalize?
Typically, no. I'd say typically your big decent grade sulfide projects will have a lower unit cost per ton material just on account of the scale. You can have very competitive operating costs, but I think the big kicker with most sulfide projects, the really outstanding sulfide projects, the big kicker that makes them work, if you will, is the byproduct credits they often have. So you start producing a couple 100,000 ounces a year of gold, it very quickly reduces that unit cost per pound.
Yeah. And in an oxide project, you can't recover the gold or the silver or the moly if there is, or so it becomes a pure play on the copper.
Well, you can do, but it involves a secondary leach, and there's ways and means to get around it. But in many of the oxide projects, you see much lower levels of precious relative to the.
Hayden, thank you so much. A real blast, a real trip round oxides and sulfides. Let's leave it there for today. Thank you very much.
Thanks, Mel.